We are going to be doing some line fitting to data today. Last Wednesday, we had started our discussion of linear functions, and that's all well and good. And if you've ever taken an algebra class, solving equations is one of those things you go, okay, I'm solving an equation. What's the point to this? Well, there is a point to it. And the point is what we're going to be doing today. So if you're out in the real world, there's probably going to be a time when you need to collect data for something or another. Something you're going to collect data for. And from that data, you're probably going to want some kind of algebraic model for it. And I can think of something that gets modeled every single day, and it's the weather. Now, I'm not going to say that the modeling of the weather is as uncomplicated as a linear model. They're very complicated models, but that's what they do. They take all the data in and they create a model, and then from that model, they do predictions. They predict what the temperature is going to be. They predict the chance of rain. They predict all sorts of things from that model. So we do the same thing here, except our models are going to be significantly simpler to determine. So we're going to first find exact models for data. That means your data is exactly linear. And since it is exactly linear, you can find an equation that fits that data. And then we'll look at data where we're going to get an approximate model. So it's data that's pretty linear, but there's not an exact model that fits the data. So we can use techniques that we learned in the previous chapter to find an equation of a line that fits the data. And then we're going to use our calculators. Because this is linear data, it's sets of ordered pairs, we can plot this on the coordinate plane. Instead of us doing it by hand, if you've ever taken a science class and you collected data and you got graph paper out, you plotted points, we're going to let our calculators plot the points. And then once the calculator plots the points, we can either estimate a line that goes through those points, or we can let our calculator estimate the line that goes through those points. And I'm thinking that's the way to go. All right. The first thing we're going to do is look at something called the first differences. And this is the difference in the Y values in our data. This is the first difference. If the first difference in the Y values of our data is constant, then that data represents a line. For example, this table gives the annual retirement payment to a 62-year-old retiree with 21 or more years of service at Clarion State University as a function of the number of years of service and the first difference of the outputs. So if we look at the first difference here of the outputs, the Y values, so our inputs is the number of years of service. So this is the inputs, the number of years of service. And the output is how much money I receive in retirement. So the output is our retirement. And if we look at the first differences in the various values for the retirement amount, we see that it's constant. So if I served 21 years at Clarion State College, my retirement would be $40,950. If I served 22 years, then my retirement would be $42,900. The difference in those two numbers is $1,950. Now, it's also important that these differences are the same. So it's important that we're going from an X value of 21 to an X value of 22, an X value of 23, that those are also constant. If I look at the difference in the retirements value from year 22 to year 23, I also see it's 1950. From 23 to 24, the difference in the retirement value is again 1950. And from 24 to 25, it's 1950. Since these first differences are constant, this is a line. So this data represents a linear function whose slope, so the first differences, is the average rate of change, or the slope. So the slope of this linear function is 1950. So if the first difference is the difference in the y's, the outputs, is constant, it's a linear function, and whatever that constant value is the slope of the equation of the line that fits your data. Okay, so now that I know the slope and I know a whole bunch of points, I can use the point slope equation to find an equation that fits this data, a linear function that fits this data. So the slope is the first difference, 1950. And we have the point slope equation. Y minus y1 is equal to m times x minus x1. And what you pick for your point x sub 1, y sub 1 is any point in your data. You could pick any point you want. So let's just pick the first point. So it's going to be what? 40,950. And we're going to plug that into our equation. So we have y minus 40,950 is equal to 1950 times x minus 21. So we have y minus 4950. We're going to distribute the 1950 across the stuff inside parentheses. What's 1950 times 21? Was that 40,950? So what happens is you add 40,950 to both sides, and you end up with y equals 1950x. And that kind of sort of makes sense that the y-intercept is 0. If you have any linear equation in this form where there's no constant being added to the term that contains the x, that means that this thing goes through the origin. So it goes through the point 0, 0, and that kind of makes sense if you're talking about retirement. If I haven't worked any years, how much retirement should I get? None. So that kind of makes sense that I'm going to get that type of equation for this particular example. Okay, so a model that fits this data is y equals 1950x. So let's talk about the model and let's talk about your data. Now the values in this table are discrete. So they give you retirement values for years of service that include 21, 22, 23, 24, and 25. They don't give you values in between. So you don't have a retirement value for 21.7 years of service. So the inputs are discrete. You can count the numbers. They're countable. As is the outputs. The outputs are also discrete. They're not continuous. So you don't get values of retirement of $41,376. So you get discrete values for both the input and the output. So the values in the table represent points satisfying a discrete function, a function with a finite number of inputs, with each input representing the number of years of service. Although only points with integer inputs represent the annual retirement payments, we can model the application with this continuous function, y equals 1950x. So for the continuous function model, we can plug any x in that we want. So it can actually be evaluated for any x, including 21.2 if you want to. Even though our data is discrete, the function's continuous. Informally, a continuous function can be defined as a function whose graph can be drawn over its domain without lifting your pencil from the paper. Okay, so on this slide, on the left, we have the graph of the inputs of our data. So we have the XY values, the year, and the retirement payment plotted on the XY plane. And the next graph over to the right is a graph of the continuous function model that we found. So the data values, when we plot those, we get a graph of discrete data values, points. But when we create the model and we graph it, we get a continuous line. So there's just trying to reiterate the difference between your data, which is a set of ordered pairs, a set of points, and then the model we created, which is actually a line that includes every point on that line. Okay. All right, are you ready to try one? So what we're going to do is we're going to create a scatter plot of this data. And then we're going to look at trying to find a linear model that fits this data. Now, if I look at the first differences, I get 1, I get 1. Here I get what, 0.6? So the first differences are not a constant, which means that this data is not perfectly linear. But I can get a linear model from the data anyway, okay? The table gives the projected population in millions of females under the age of 18 projected for the years 2020 through 2060. We're going to draw a scatter plot of the data with the X value of each point representing the number of years after 2000. So we are aligning our X data, our input data, to be the number of years after 2000. So if I go back, then 2020, we're going to input the number 20. The number of years after 2000 for 2020 would be 20, right? Graph then the equation y equals 0.1x plus 36. And let's see how good a fit that linear model is to our actual data values. And then we're going to use a piece of uncooked spaghetti. No, I'm not going to do that. But you could use a straight edge and try to get the best fit line just looking at your data. It's not the most efficient way of doing it, but it is a way of finding a model of your data. All right, so we're going to put this data in our calculator. So what we're going to do is we're going to put the year, the input, in one list, and we're going to put the population in millions in another list. That's our output. But we're aligning this data to the year 2000. So our first list is going to start at 20 and go through 60. So here is the actual data you are going to put in your calculator. And I used L1 and L2. Why not? Do you remember how to clear your list if you have anything in your list? What do? You go up and highlight the list name, hit the clear button, and then drop back down, and it should be clear. So put this first column of data in one list and the second column of data in another list. I'll give you a few seconds.
So why on what you said we'd put, why, so like on this one, it only goes to 40, so why do we go above 40 in our list?
You got a second list over here on the side, 45.
Yeah, like, so like the year goes from 2020 to 2040, you know, and your list goes from 20 to 60, like,
Because I've got two sets of years here.
oh, okay, now I see.
The table is kind
Okay,
of
yeah.
wonky.
Okay,
You
never
get the
mind.
first set and the second set, yeah. All right, how are we doing? Have we got it in? I didn't even ask if you remember how to put your data in a list, but you were all working away, so I figured you remembered how to do it. Okay, so let me go to my calculator. So I'm going to go to my stat, edit, and my data is in L1 and L2. All right. So now we want to create a scatter plot of that data. So I'm going to exit out of my list. So do a second mode to get out. And then I'm going to go to my stat plots. So I'm going to go second, y equals, and I'm going to turn on my stat plot. Okay, I've got my plot on. I've got two plots on because I was doing this in statistics. So I'm going to go turn that second plot off real quick. We were plotting in the stats class. All right, let me get out of here. Go back to my stat plot. And I'm going to make sure that plot is a scatter plot. So the type, I want the first type, the scatter plot. So I'm going to make sure that is selected. And then I need to give my calculator where I put my input values, the years. I put mine in L1. So I'm going to go down and do second one. And then I put my output, my number of millions of women in my Y list in L2. So second 2. Okay, so I'm good to go there. Are y'all good? Now, what I probably should do real quick is go see what's in my Y equals. So let me get out of here. Let me go to my Y equals. Nothing's in mine. Do you have anything in your Y equals? If you do, clear it out because you don't want to graph that yet. Okay, so now we're ready to go. So the easiest way to graph a scatter plot is to use a Zoom 9, Zoom stat, and that will set your window according to your data. So if I go to the Zoom button, Zoom number 9 stat, we should get a scatter plot. Is that what yours looks like? And you can see it's not perfectly linear, is it? Do you see these points right in here? Get my mouse working here. Right in here, it looks like we've got a couple of points, maybe 2, that are not exactly on a straight line. So it's very linear. I mean, it looks like a line, but you got a couple of points that are not quite on a perfectly straight line, and that's fine. It is approximately linear. Okay, so the next part of this problem is they want you to graph the equation of a model over the top of this graph. So let's go back to the slides. And they want you to graph y equals 0.1x plus 36. So you're going to go to your y equals, and you're going to type in 0.1x plus 36. So I'm going to run over there and type it in. So I'm going to go to my y equals, and we had what, 0.1 x plus 36. And then just hit the graph button. So what's your conclusion about that model? It's not a very good model, is it? Could you find a better model? And the answer is yes. Now, taking my piece of spaghetti out, if I were to draw more, a line that more fits the data, would it do something like that? Do you think?
Yeah.
So what I could do is I could pick 2 points, 2 ordered pairs on that approximate line I drew and find the equation that fits those ordered pairs. And if you've ever taken a science class in your previous life, this is probably the way you did it. So you find 2 points on what looks to be the approximate line and find the equation that fits that. That's what we're going to do. And then I'll show you how you can let the calculator do it. Okay, so let's go back over to my slides. And let's find a couple of points. And the couple of points we found were 25, 38.2, and 60, 43.6. And typically you do find 2 points that are somewhat far away from each other. And we found like one of the first points and then one of the last points. That's what you want to do, is get 2 points that are fairly far apart. And now we're going to go through finding the equation of the line using the point slope equation. So the first thing we need to do is find the slope. And the slope is the change in the outputs over the change in the inputs. And what do we have? 43.6 minus what? 38.2 over what are the change in the inputs? 60 minus 25. And we just want a decimal approximation to this. So a 3 point to the nearest thousandth will be fine. So I'm going to go over to my calculator and I'm going to do this on my calculator. Okay. And I'm just going to use my fraction button, although I could also use parentheses. Let's do it with parentheses just for practice. So I'm going to divide that 43.6 minus 38.2 by the 60 minus 25. So I'm going to use parentheses. So I have 43.6 minus 38.2. I'm going to close those parentheses and I'm going to divide that by, what do I have in the denominator? 60 minus 25. And I do need to put both numerator and denominator in parentheses. Otherwise, your calculator doesn't understand that it needs to take that difference in the numerator, that difference in the denominator, and then divide them. 0.154. So if I'm rounding this to 3 decimal places, the 4 is in the 3rd decimal place. I go 1 decimal place to the right, correct? It's a 2. If that number to the right of where I'm rounding off to is 4 or less, I just truncate. I just drop all the numbers and round off to 0.154. Okay, so the slope is approximately 0.154. And I use a squiggly equal just to say that is an approximation. Okay, and then we're going to use the point slope equation. Y minus y1 is m times x minus x1. And I'm just going to use the first point in this point slope form. So I'm going to use the 25, 38.2. So y minus 38.2 is equal to 0.154 times x minus 25. Is that correct? Okay, and you're probably going to need your handy dandy calculator, and I am going to need my handy dandy calculator because I used the other number. So y minus 38.2 is equal to 0.154 x. What's 25 times 0.154? Never use your phone. Do as I say, don't do as I'm doing. 3.85, is that what you guys get? And then we're going to add the 38.2 to both sides. And I get y is equal to 0.154 x $34.35. Is that what you guys got? Okay, now let's go graph that. Now, you can just graph this in Y2. And if you got a color, some of you have a color, it'll graph the second line in a different color. So that can be quite beneficial for you to see the first approximation or the first model of your linear function and your second model. So let's go over there and graph it. And I am going to graph it in my Y2. So I'm just going to go arrow down to Y2. And I'm going to graph that second model. So 0.154 x, is that correct? Plus 38.35, 38.35. And then just hit the graph button. Oh, I got a mistake somewhere. What's my mistake? What did we do? Oh, 34. It helps if you put in the right number, doesn't it? It's 34, is it not? Is that better? I think so. Much better, much better, much better. So the red line is the model we just found using 2 points. Do you think that's a better model than the original model we were given? Fits the data much better, doesn't it? Okay. Can your calculator do this? And the answer is yes. And aren't you glad you're here today? Because I'm going to tell you how to do it. I'm going to get out of my graph. Oops, I'm going to quit. And then I'm going to actually graph that line in Y3. Just because I want the original model, the model we found from the 2 points, and the third model that your calculator is going to calculate all on the same graph. Typically, you're going to graph your scatter plot and then the calculator models in Y1. I'm going to do it in Y3 just for kicks and giggles. Okay, you are going to go to your stat menu. And you're going to go over to the calc menu in your stat menu. And you're going to look at number 4. Number 4 says lin reg parentheses ax plus b. What the calculator is going to do is it's going to run a linear regression. That's what that stands for. Linear regression on your data that you put in. And it's going to actually iterate faster than you can even blink to find the line that fits your data the best. Okay, so we're going to arrow down to number 4. And then I have to look at what data my calculator needs. It needs the list where you put your input values. Where did you put your X's? I put mine in L1. So I'm going to change that to L1. Second one. Where did I put my output data, my Y values? I put mine in L2. So I'm going to tell my calculator L2. I don't have a frequency list. And the last thing I need to do is to tell my calculator where to put this equation so I can graph it. This is the hardest part of this because you have to go through multiple steps to find where to put this, okay? So I'm going to store that regression equation in one of my y equals. So what you do you see the variables menu just to the left of your clear button? You're going to go there. And if you look at the top, the second menu over, do you need to leave? Okay. Oh, you can. The second menu to the right is your y variables. You're going to go there. And we are graphing functions. So you're going to go to your function menu. So we go variables, y variables, function. And I'm going to graph that in Y3 because I put stuff in Y1 and I put stuff in Y2 and I want to see everything on the graph. So I hit enter and it's ready. So it's got where the X values are coming from, where the Y values are coming from, and where it's going to store that regression equation. So I'm going to hit calculate. And there's the regression equation. Okay, what information do they give you? Now, you may not have the R squared or the R yet. I'm going to tell you how to turn that on here in a minute. So you may just have y equals ax plus b. You may only have the a and the b. Okay, don't worry about that. Okay, so what's a? A is the slope, 0.155. Is that approximately what we found when we used the 2 points? Pretty close. B is the y-intercept, and that's where we're off a little bit from our estimate. So B is approximately 34.278, which is a little bit different than what we got from our 2 points. Okay, now I stored that in Y3. So if I hit the graph button, I should see my scatter plot. I should put that first, see that first model that we put in, the 0.1 plus 36, whatever it was. The second model we found by taking the 2 points, and then the model the calculator found. What do you think is the most accurate? That right there. That is the most accurate model of that data. So if I hit the graph button, maybe if I can get my mouse to work, there it goes. So there's the first model, the second model, and then the third model on my calculator was graphed in black. And it's pretty close to the model we found using the 2 points, isn't it? Very close. Now, if I go to the y equals, I can see the model that we got from finding the slope point form was 0.154x. Well, we get, the calculator gets 0.155. And we got a y-intercept of what, 34.35, and the calculator has 34.28. So pretty close. Now you're good. Do the whole rest of this section's homework. Okay, let me go back to my slides. A procedure that defines the best fit line as the line for which the sum, you don't really care, the sum of the squares of the vertical distances from the data points to the line is a minimum. So what your calculator does I was gonna say, back in my day when we did this by hand, which we did, can you imagine? Is your calculator, as I said, it finds the line that has the optimal distance from each point in your scatter plot. So it goes through in a blink of an eye, and it makes that line where it's just the optimal distance from each point. Okay, all right, so let's do another one, shall we? Now we're gonna have to clear a bunch of stuff out to this second model. The total US population for selected years beginning in 1960 and projected to 2050 is shown below with the population given in millions. So we want to graph this population data. And we need to decide what we're going to align our year to. Is it going to be since 1960? Is it going to be since 1950? So we're going to let the calculator, excuse me, the problem tell us what to do. So we're going to align the data to represent the number of years after 1960. Well, if that's true, this is going to be 0. And this is going to be 5. This is going to be 10. And then you get over here and you got some wonky data. So 98 would be 38. 2000 would be 40. And 2003, what would that be? 43. And so we have a gap, and then we have a huge gap. We don't have any data for 22 years. There's a huge gap in the data collection. So this would be what? 65? And that would be what? Is that 110? So we have some huge gaps in our data. So that's what we're going to put in. I'll put this up here in just a second so you can put it in. Then we're going to create a linear equation that's the best fit. So we have to graph the scatter plot first, get the scatter plot, and then find the equation of best fit. And then we're going to graph the scatter plot and our model on the same graph, just as we did before. And then we're going to change the alignment. And I'm going to show you how to do that. What if we change the alignment of our year from starting at 1960 to starting at 1950? You do not need to re-input your data. You can let your calculator recalculate the alignment. I'll show you how to do that. Okay. So what you're going to put in, let's go back over here. Let's see if I can write this neatly.
2050 is what?
Well, it is if you can add. Subtract. Which apparently I can't. So you're going to put in 0, and you can put this in L1 and L2 if you want to, wherever you want to put it. I think I have mine in L3 and L4, just because I did want to erase my data. So this is going to be what, 5, and this is 10, 15, 20, 25, and thank you for correcting me because I don't want the recording to go out with me saying the wrong thing. So is this 30 and 35 and 38, correct? 40, 43, 65, and 40 and 50 is 90. So I'll let you get that data in your calculator. So put the year in one list and the population in another list. Okay, how we doing? I put my data in L3 and L4 because I didn't want to erase the previous problems data. I am going to go into my y equals and clear all that stuff out because I don't want to graph my scatter plot and those lines on the same graph. Okay, so I'm going to go to my scatter plot. So second y equals, make sure the scatter plot's on, and then I need to change my x list to my y list to reflect where I put my data, which was L3 and L4. All right, once I have that in my calculator, I'm again going to do a zoom 9, zoom stat, because my data's changed. And I want my calculator to adjust the window to the current set of data. So I'm going to go zoom 9. And it's in kind of an interesting shape here. It looks fairly linear down here with the first set of data. And then we've got those two kind of afterthoughts, big skip in the number of years where we took data. And so as a person that's investigating this data, you would want to know why there's such a gap there. What happened that gave us that huge gap in our data collection? Maybe just someone forgot they were collecting data. I don't know. But there's a huge gap in the data collection. All right, so now I'm going to let my calculator calculate the linear function that best fits this data. So I'm going to get out of my graph. And I'm going to do something right now to turn on that R squared and that R when I run the linear regression, so we can talk about it in a second. So I am going to go to my mode button. All sorts of fun stuff in the mode screen. But down here toward the bottom, do you see the stat diagnostics? Do you see that? You want to turn that on. So arrow down to highlight the stat diagnostics, and then make sure you turn it on. And that'll turn on that R and that R squared in the linear regression screen. All right, so make sure that's turned on. All right, I'm going to get out of the mode, second quit. And now I'm going to go to my stat menu. And I'm going to go to the right, to the calculate menu, and I'm going to calculate number 4, the linear regression. For me, I put my data in L3 and L4, so I am going to change that. Second 3 for my X list, second 4 for my Y list, and then I'm going to store my regression equation in Y1 because I cleared everything out, so I'm going to put it in the first Y equals. So I'm going to go to my variables menu, which is just to the left of the clear button. I'm going to arrow to the right to the Y variables because that's where I'm going to put this. And number 1, the function. And I'm going to put this in Y1. So I hit enter. So now see if I'm good. My years are in L3. My population is in L4. I don't have a frequency list. And I'm going to store that regression equation in Y1. So we're going to now calculate. Okay, so in this list of numbers, the first number, A, is the slope of this linear function. So the slope of this linear function is approximately 3, correct? even if I were to round off to 2 or 3 decimal places, it's gonna round up to 3. The y-intercept, where this thing crosses the y-axis, is 169.348. And then we've got some information here, r squared and r, which we'll talk about in a moment. All right, so now we're going to graph. When I hit the graph button, it's going to graph that scatter plot and this equation of the linear regression. Now, if I were a statistician, I'd probably go investigate that last point, that one right there. It's a little bit off from my regression, so I might investigate that point. As a matter of fact, I said earlier, I would investigate 2 of those points, and I try to figure out what happened with those 2 points. Okay? So now we have a scatter plot, we have a linear model. Let's go back to that r and r squared. Now, I've cleared it out, so if I get out of my graph, it's no longer in my home screen, but I can recall it. So if I go to my variables menu and I go down to number 5, statistics, that's what I just calculated. If I go down to statistics and I calculated an equation, a regression equation. So if I go over to equation, EQ, if I want to recall the regression equation, I can just hit number 1. But what I'm interested in is that R value. So I'm going to go down there and highlight that, hit enter, and then hit enter again. Okay, so what is this number? This number is a measure of how good a fit your model is to your data. This number is always between -1 and +1. So it's called the correlation coefficient. Its value is always between -1 and +1. If R is equal to 1, your model is a perfect fit to your data. Perfect. It's a perfect linear model. The farther away it gets from 1, the less perfect a model it is. -1 is a perfect negative correlation. If R is positive, the slope of your line is positive. If R is negative, the slope of your line is negative. So if R is positive, the line rises from left to right. If it's negative, it falls from left to right. -1 for a correlation coefficient is perfect negative correlation. It's a perfect line with negative slope. Okay, so that's what R means when you see it. Okay, so 0.98 is a pretty good linear model for this data. That's pretty close to 1, so this is a good fit for our data. So our linear model, which is, if I go to the y equals 2 point, well, it's approximately 3x plus 169 point something, is a pretty good model of our data. All right, now let's go back to our slides for a second. It says, align the data to represent the years after 1950. So instead of 1960, let's use 1950 as our starting point. Well, if our starting point is 1950, then our first list would be what? 10, 50, what would that be? 50, is that 15? 20, etc. So you need to add 10 to each one of these. Okay, there are 2 ways you can do this. So I need to add 10 to my X list. Okay, so I'm going to go look at my stat menu. And there's my L3 and L4. So what I can do, if I need to realign the L3 data, I can go over there and add 10 to it. Okay, what does she mean? So I'm going to go over to L3. That's where my data is. I'm going to arrow up, and I'm going to change that to L3 plus 10. I want to add 10 to every point in that list. So what I do, once the L3 is highlighted, I go second, 3, and you can see down here at the bottom, now I've got L3, and I'm going to add what, 10? I'm going to align that data to the original data plus 10. And when I hit enter, what does it do? Now, the other thing I could have done, I'm going to go take that out. So I'm going to change that back to L3. Whoops, I got to do L3 minus 10. Sorry about that, folks. I did change it. So 3 minus 10. So that's the original set of data. What I could have also done is moved over to L5 and then made the inputs in L5. So I can move to L5, highlight L5, and change that to L3 plus 10. And that'll do the same thing. And, you know, it's 6 of one, half dozen of the other. If I want to preserve the original alignment, I'm going to do it that way. If I don't care, I'm going to change the L3. I'm going to go change the L3. So I'm going to go back to L3, go up and highlight it, and add 10 to it. So L3 plus 10. And now, once I have that, I have to do a zoom stat again. But I also need to clear out the model. So I'm going to go to my y equals and clear out my model. Clear that out. And then I'm going to do a zoom 9. And the data looks the same because my calculator's resumed my window. So it looks the same. If I turn the trace on, I can see that it's changed the input to 10, the 15, 20, 25, 30, 35, 40, etc. Okay, so now when I create the regression equation, the slope should be the same. So it shouldn't matter that I changed the inputs by 10 years. The slope should be the same, but it should change the y-intercept. So let's get out of here. Let's do a stat calc number 4. And it's still on L3 and L4, but I always have to put the regression equation back in. So I'm going to store that in Y1. So I'm going to go variables, arrow to the right to the Y variables. I want a function variable, number 1. So I hit enter, and I'm going to store that in Y1. And then calculate. Slopes 3. What was our previous y-intercept? 1 something. So it changed the y-intercept. Okay, so if I look at the graph now, the graph should be identical to what I did before. Okay, so use both unrounded models to estimate the population in 2000 and 2010, and they should be equivalent. No matter how you align the data, the output for a given input should be the same. Okay, so let's go over to our calculators. So we're finding for 2000 and 2010. So using the model that I have, we're aligning since 1950. So 2000 would be X is equal to 50. Is that correct? If you're in the year 2000 and your data is being aligned since 1950, would that be X is equal to 50? So can you find the Y value for a given X? Do you remember how to do that? Okay, if you go to your calc menu, number 1 is value. It will find a Y value for a given X. So if I hit enter, what am I trying to find the Y value for? I'm trying to find the population for the year 2000 for data that's aligned since 1950. So is that 50? So what's the population? 289.187 thousand. Now, real quick, I'm going to go fix my data back. I'm going to realign it. I'm going to regraph it. I'm going to refine the regression equation. Variables, Y variables, function number 1. And graph. Okay, now let's find for the year 2000. So since I'm aligned to 1960, the year 2000 would be 40. So we're going to find second calc value for X is equal to 40. Is that the same value? It should be the same Y value. For the year 2000 is going to be the same no matter what alignment you use. What was the other one? 2010. So if this was aligned since 1960, would 2010 be 50? Is that correct? Yes. So if I calculate the Y value, so second calc, the value for X is 50. Now, if you still have the other data in your calculator, you would be aligned from 1950. So 2010 would be 60. So if you calculated on your calculator right now, you'd calculate for X is equal to 60. Do you get 319,000? Is that what you got? Is that what you got? Man, you might actually get out of here early today. So here is the model that we found. That's not what we got. That's not what I got. Did you get that? Did I put in something incorrect? Probably. I don't think I got 2.6. Did I get 2.6? Oh my, 2.9. So I apparently made a typo somewhere. Nobody's yelling at me. Where did I make a typo? Like watching paint dry. So those are good. How about my years? I think that's actually, yep, I sure did. And nobody yelled at me not once. Oops, better put 90 in there. Whoops, I can't type. Is that better? So let me do that again. So, second, quit. Second, calc. Second, quit. Stat calc. One variable statistics, excuse me. Store that in Y1. I'm mumbling to myself. Okay. Is that better? Is that what you guys got? And as a matter of fact, now that I have the data in the calculator correctly, is that even a better linear fit than the previous set of data that I plugged in incorrectly? 0.997 is pretty close to 1. So this is almost a perfect fit. If I do a zoom 9, and if I calculate the year 2000, I'm aligned since 1960. Would that be 40? So normally when I input data into my calculator, I check. Apparently I checked, but I can't subtract. Apparently, that's my problem. All right. I think that's about it. Are there any questions? We talked about goodness of fit. Any questions? All righty. Well, we'll see you on Wednesday. And I will try to make sure that I don't make mistakes inputting data.